Hello, my name is Matthew Kemp and I'm studying for a PhD or DPhil in Earth Sciences at the University of Oxford, and today I'm going to take you on a journey to the centre of the Earth. In today's video lesson I hope you learn three main things. Our first objective is to understand that the Earth has a dynamic interior and that it's always moving and changing. To learn that seismic waves can be used to look inside of the Earth, and to discover that the Earth's interior affects the surface in a variety of different ways. Now, I said I was an Earth scientist, and I really love Earth sciences because it's so varied. It's not just geology and rocks, though rocks are pretty cool. It uses loads of other techniques from a lot of other different subjects, such as physics and chemistry and biology and maths and even geography and computer sciences. It uses lots of these different techniques to try and answer big questions about the world, such as what in Earth is going on beneath our feet. Now, before we get started, I'd like you to do a little activity. So pause this video for 1 minute and I'd like you to draw what you think the structure of the Earth is. So just draw a circle and then maybe put some layers in, I don't know, but just give it a go. I want to see what you can come up with before we get started. Off you go. Hopefully you got on okay with that, and perhaps you came up with something a bit like this sort of layered structure. And though this is pretty much correct, there are still big questions about the large-scale processes that are going on beneath our feet. And we're interested in this because Earth is a very unique place. It's the only planet we know of that can harbour life like us. And we want to work out how the processes inside the Earth have created a surface that life can live on. We want to work out what those processes were doing in the past, how they're affecting the Earth now, and how they're going to change into the future. Let's start off with this very simple view of the inside of the Earth, this layered structure. At the very centre we have the solid iron inner core. Around that is the liquid iron outer core, and around that is the solid rock mantle. And then on the surface is the very cold, thin crust that we live on. The very centre of the Earth is very, very hot. It's about 5,000 degrees Celsius. And over the last 4.5 billion years, it's been slowly cooling down. And this heat loss has been providing the energy that drives all the dynamic processes that are going on inside the Earth. If you look at this diagram, you can see that the outer core is heating up the bottom of the mantle. The bottom of the mantle therefore becomes hotter, it becomes less dense and starts to rise. When it eventually reaches higher up, nearer the surface, it starts to cool down, it becomes more dense and then starts to descend again. This is called a convection current, and this means that the mantle, the solid rock part of the Earth, is actually moving at very, very, very slow speeds. It's a bit like if you imagine a lava lamp. Now, to try and work out all of these different processes underneath the Earth, we can try a variety of different methods, and one of them is digging. Now, how deep do you think the deepest borehole is? Have a guess. Ooh, it's 12 kilometres, which is quite deep, but actually that's less than 1% of the radius of the Earth, which is 6,371 kilometres, so it's barely even scratched the surface. And we can't really get any deeper than that because it gets too hot and too highly pressurised. Everything would just break. So we need something else to go inside the Earth for us, to tell us what's going on down there. We can't go inside the Earth, but seismic waves can. They're like our scouts. They descend into the Earth, and when they pop up back at the surface, we can detect them and they can tell us about the journey they've been on and what they saw along the way. Seismic waves are generated by earthquakes, when you have two large rocks pushing against each other or trying to scrape past each other, but they can't, so they're building up a lot of tension, and then suddenly they move, they break, and they send out that energy as seismic waves, these vibrations into the earth. Imagine dropping a stone on a pond and seeing the ripples spread out, but with seismic waves these ripples are in 3 dimensions. Now, earthquakes can be very destructive events, but we can use the seismic waves that are generated by them to work out what's going on beneath our feet. Seismic waves come in a few different kinds. You've got the surface waves, which vibrate along the surface, and then you have the body waves. Those are the ones that actually go inside the earth, and there's 2 main kinds of them. You have the P waves. They vibrate in the direction that they move. So they're called longitudinal or compressional waves, and they're the fastest. And then you have S waves. They vibrate perpendicular to their direction of motion. They're called transverse or shear waves, and they're slightly slower than P waves. We can use these very sensitive pieces of equipment called seismometers to detect these seismic waves when they go past. Here's my friend Jenny, who's in Iceland digging a big hole to put a seismometer in it. And when a seismic wave goes past, you get various wiggles. And these wiggles can tell you about the journey that that seismic wave went on. As you can see in this diagram, the very first thing to come in, because it's the fastest, is the P wave. And then you have another wiggle a bit later on, which is the S wave. And then later on than that, you have those big surface waves. Scientists have been using seismic waves to investigate the inside of the Earth since pretty much the beginning of the 20th century. For example, in 1906, Richard Oldham used seismic waves to discover the core. He knew that S waves, those transverse waves, couldn't travel through liquids. And when an earthquake went off, in this diagram the yellow star, all the seismometers on the opposite side of the Earth, in that red arc, never detected any S waves. It was the S wave shadow zone. So he knew that there was something in the middle of the Earth that was blocking those S waves. Moving slightly forward in time to 1936, you have an amazing seismologist called Inga Lehrman, and she detected that there were these very small seismic waves which went down into the deep, through the mantle, through into the liquid outer core, but then bounced off something inside of it and then went back up to the surface. She proposed that there was a solid inner core within the liquid outer core. Since the 1970s and 80s, a lot more seismometers have been put across the world. This was initially due to testing for nuclear weapons, seeing if anyone was setting them off, but it has also led to a proliferation of data which we've been able to use to look inside the Earth. If you have, say, the position of where the earthquake went off, the source, and you also have the position of the seismometer, and you know the direction that that seismic wave went on, you can have a distance. And if you know how long that took, you have distance over time, that gives you velocity. That means that you can start building up these velocity maps of how the seismic waves change in velocity as they go through the Earth. It's a bit like taking an X-ray of the Earth. In this diagram you can see lots of red and blue bits. Those red bits show where seismic waves are slower, and that's possibly because they're moving through a hotter region. And the blue bits are when those seismic waves are travelling faster, so they may be moving through a colder region. Also, we can detect when those seismic waves hit boundaries, because they can either reflect off them, so they bounce off them, or they can refract, so they change direction when they go through them, or they can convert from one form to another. So it could be a P wave, and then it hits a boundary and turns into an S wave. We can use these seismological maps along with other parts of data, such as geodynamic models, which can model how liquids move very slowly through the Earth, or geochemical experiments, where we can look at different compositions of rocks and see how they may behave down inside the Earth. and also mineralogical experiments where you essentially take some rocks and squash them down really hard and heat them up to the conditions or similar to the conditions that are deep inside the Earth and see what happens. By combining all of these different pieces of information, we can start making a good picture of what's going on inside the Earth. Now it's time for you to have a go. Follow the link at the bottom of the screen to the IRIS website. Now, IRIS is an amazing repository of loads and loads of seismic data. And they have this great simulator there where you can set off seismic waves, see them travel through the Earth, and then see what the seismometers would pick up at different positions across the Earth. So yes, just pause this video for about 2 minutes, have a go yourself, and feel free to go back to it later as well. Off you go. I hope you had fun with that earthquake simulator. And now I'm going to take you on a voyage into the deep Earth to show you various structures that have been detected using seismic waves. And hopefully show you that the Earth isn't just this simple layered structure, but that it is dynamic and constantly changing, forming all of these new, weird and interesting structures. We'll start off right at the centre, at the solid iron inner core. When the Earth first formed, the core was completely liquid, but over the last few billion years, as the core has cooled, a solid iron inner core has formed, and it grows about 1 millimetre a year, so very slowly. That inner core boundary is probably very mushy, maybe it's spiky like a tree. We're not quite sure, but we're investigating that. We then have the liquid iron outer core, and this is convecting, so it's sloshing around, and this actually generates the magnetic field that we can use on our compasses to try and find our way around, but it also protects us from charged solar radiation, which is really important for the development of life. Let's now hop up to the surface of the Earth. Now we know that the surface of the Earth is split up into various tectonic plates, which are made up of the crust and the very top bit of the mantle. These move across the Earth's surface, and at their boundaries we often have earthquakes occurring. When two tectonic plates collide, they can form mountains, and then sometimes one can descend underneath the other. They will then keep descending down into the mantle, and these are called slabs. And we can image them using seismic waves because these slabs are often colder, and therefore the seismic waves travel faster through them. So they're those blue bits in those sort of X-ray models that I showed earlier. These descending slabs really govern the movement of the plates on the surface, which can change the whole way that the continents look on the surface. When these descending slabs reach the core mantle boundary, the very base of the mantle, they will form a tectonic plate graveyard. Ooh. This graveyard will then slowly heat up due to the heat loss from the core and start to rise in mantle plumes, which we'll see next. These hot upwelling mantle plumes rise from the base of the mantle up to the surface. They are often seen as red in those X-ray seismic models because they're hotter and therefore seismic waves travel slower through them. They bring material from the very base of the mantle up to the surface, and they also cause hotspot volcanism on the surface of the Earth. They generate islands like Hawaii in the middle of the Pacific Ocean. These plumes are anchored to the bottom of the core mantle boundary by these ultra-low velocity zones, which are very dense, hard to image blobs of material. These are often around the edges of deep mantle mountains. These mountains are also called large low velocity provinces, so seismic waves travel a lot slower through them, showing up as red on those X-ray diagrams. And these massive blobs of material which rest on the core mantle boundary show that this boundary, this surface of the core, is just as topographically interesting as the actual surface of the Earth. Finally, we have the mantle transition zone, which is between 410 kilometres and 660 kilometres depth. It's the boundary between the lower mantle and the upper mantle, and it affects the movement of descending slabs and upwelling plumes, and often filters different materials out. It's quite an important and interesting boundary. Now it's time for you to have a go. Follow the link at the bottom of the slide to Ian Rose's Interactive Earth, where you get a slice through inside the Earth and you can generate some hot spots, some upwelling mantle plumes, and some cold descending slabs, and see how the inside of the Earth will convect. You can also pause it and send an earthquake through to see what a seismometer would see. You have 2 minutes, off you go. We've learnt all about the weird and wonderful things that are going on inside the Earth, but how do these processes affect us on the surface? Well, if we start at the centre, we have the inner iron core, which is cooling. This heats up the outer core, which is a liquid iron, and this generates convection currents, which in turn generates a magnetic field. This magnetic field can protect us from charged solar radiation, which is quite important because if you look at planets like Mars, which don't have this dynamic magnetic field, solar radiation has stripped the atmosphere off Mars, and as far as we know, life can't survive there anymore. The cooling of the outer core generates convection in the mantle, which manifests itself as these rising mantle plumes, which when they reach the surface cause hotspot volcanism, creating volcanic islands and various volcanic regions. And these volcanoes let off a lot of gases into the atmosphere, and that changes the climate. The other aspect of mantle convection are descending tectonic plates. This drives the movement of the tectonic plates across the surface, and when they collide they can form and build mountains, and these mountains can affect the atmospheric movements. They can also move where the continents are, and this can affect the ocean circulation as well. And all of these different factors influence where and how life survives on the surface. So as you can see, the whole world is connected right from its core to the surface. So there you have it. We've reached the end, and now I'd like you to do exactly the same as you did at the beginning. I would like you to draw a circle and draw what you think is going on inside the Earth, now with all of the knowledge that you've hopefully gained over watching this video. I'll give you a minute. Off you go. Perhaps you got something a bit like this. Don't worry if you forgot anything though, because you can go and watch this video again. In summary, I hope you've learnt the following things. That the Earth's interior isn't just a set of layers, it has lots of intricate structures and is constantly moving and changing with time. That we can use seismic waves to look inside the Earth and a variety of physical and computational experiments to model the interior. And that deep Earth processes have a big impact on the Earth's surface, from the movement of continents to the circulation of the ocean and atmosphere, and ultimately to life itself. I'd like to leave you with a question. How can we use the same techniques to work out what the interiors of other planets are like? To start you off, I suggest you look up about Mars and the InSight mission, which landed on the surface of Mars recently. They put out a seismometer called SEIS, and it's been trying to detect Mars quakes, along with the impact of various other missions onto the surface, such as Perseverance. If you've enjoyed this video, then there's various other resources which I could recommend to you. Firstly, there's the Deep Earth Explorers website from the University of Cambridge. A lot of the information and pretty much all of the images that I've used today are from that website. So you can delve deeper into all of the things that I introduced, and there's lots more activities as well, such as building a seismometer out of a smartphone. There's also a lot about what life is like as a researcher. Also, if you'd like something hopefully quite fun and memorable, I've put all of the information that I taught you today in this video into a song called From the Crust to the Core. So if you follow this link to my YouTube channel, you should find that song on there. If you'd like to go back to basics and think about that very basic structure of the Earth that we talked about at the beginning, then you can go to the Parsquake Educational Videos website. And if you follow on with that course, you can learn even more about earthquakes and earthquake hazards. And finally, if all of this has really excited you about earth sciences and you do any of those many subjects, physics, chemistry, maths, biology, geography, computer science, all those different things, then perhaps you'd like to do earth sciences at university. And if you do, I would recommend going to this website, which tells you all the different courses that are available in universities across the UK that are accredited by the Geological Society. And I would recommend that the University of Oxford does a really good earth sciences course, but there are many others. I hope you've really enjoyed going on a journey to the centre of the Earth today, and good luck.